Hello and welcome to this episode of SPSS one-on-one series with the Warrior Analytics. In the previous episode, we looked at an overview of Poisson regression, the different models available. And so today, we are going to look at Poisson regression analysis procedure in SPSS. As usual, we start with checking for assumptions. We build the model, and then we do a final model check. So let's get started. So in this episode, we are using a fixtures data set. I have included a link in the description of this video where you can download this data for your practice. So in this data set, we have a count outcome called visits, number of visits. Remember, for Poisson, you should have a count outcome, a non-zero count outcome. So it is 0 and above. Then we have 3 independent variables that are we want to use to predict the number of visits someone makes to a hospital. So firstly, we check for assumptions. And the major assumption in using Poisson is checking whether the mean is equal to the variance. To do that, we can start by running simple descriptive statistics. That's under analyze. You go to descriptive statistics and frequencies. We don't need to display frequency tables, but we need to get for the variable, for our outcome variable, number of doctor visits. We want the statistics, that is mean, and then the variance here. Then you continue and click OK. When you look at our mean, it is 2.43 and the variance is 2.77. They are not the same, but roughly the same. It can give us an idea that, okay, maybe there is the mean is equal to the variance, but we also have a statistical test that you can use to test whether the mean is equal to the variance, whether your data follows a Poisson distribution. So to do that, we go to analyze, you go to non-parametric tests, choose legacy dialogues, and then check the one sample KS test. So under this, we are going to put there our outcome variable, the count outcome variable, which is the number of visits. Then under Poisson here, we are going to, under test distribution, we are going to test whether it follows a Poisson distribution, and we put in the mean of our variable. In the previous one, we had obtained that is 2.43. Okay, so we put here 2.43. Under options, yeah, you can ask for descriptives, click continue, and then say OK. In our output here, we have the descriptives showing us we have 300 sample size. The mean is this. We have this. We are interested in the one sample KS test, which is testing whether the test distribution is Poisson. Okay, and it is telling us that we specified, it is us who specified the mean 2.43. So based on this, we are interested in a p-value that is not statistically significant. Remember, the null hypothesis here is that test distribution is Poisson. If we have a non-significant value, we fail to reject that null. So our data is fit to be tested using a Poisson regression. So that is how we can test for assumptions. Either just running the descriptives here or running the one sample Kolmogorov-Smirnov test, which we are interested in a non-significant value. So next, we look at building the model. And building a model involves 3 major steps. Choosing which variables you're going to include in your multivariate analysis, checking for interaction, and checking for confounding before you come up with your final model. We have previous videos in logistic regression where we explained this in depth. I highly recommend that you look at those. Here we are going to assume our sample size is enough and we are using all the variables in our model. So to run a Poisson regression analysis, simply go to Analyze. Usually we would expect to find it under regression, but instead it is under generalized linear models. Generalized linear models here. Click on it, and then in this dialog box we have different tabs where type of model, response, predictors, up to export. In the first tab we choose the type of model which we are going to use, and our outcome is a count, so we can use Poisson log linear. If it was a scale, it shows you which models you would choose. If it was ordinal, and so forth. So this one we are using log linear. Then we go to the next one, response. Our dependent variable, we are putting it here, number of doctor visits. Then we proceed with predictors. Factor variables, the categorical variables, we put it under the factors box. So we have these two variables that we are going to put under factors, and then covariates, we are going to put there age. Then under model, we are going to use all these variables into our model as main effects. So we are putting them there. And then estimation, we are leaving it as it is. Then under statistics, we are going to check one extra box here for include exponential parameter estimates. Click on it and then continue. So in our output, we first have the model information. We can see that we are modeling number of doctor visits. We are using the Poisson distribution with the log function. 300 participants. Our categorical variables are given in here. The continuous variable characteristics are given. And then we look at the goodness of fit test table. This one is the goodness of fit test table. Is more of testing for you the assumption of whether the mean is equal to the variance, whether there is over dispersion or not. The value, we are interested in a value as close as possible to 1 to show that there is no over dispersion. So this value of 1.015, that's okay. Some scholars recommend a value between 0.9 to 1.1. That one is considered good. So we have here omnibus test, which compares a null model and a model with our predictors. We are interested in a statistically significant value, which shows that our predictors have significantly improved our model. Then we have here test of model effects. This one shows you among the variables that are in your model, which ones are statistically significant. From this, we can see that gender is significant, and then pollution level is significant, whereas age is not significant. So we are going to go ahead and interpret these two variables. In our last table here, we have parameter estimates, and there is quite a lot of information in this. First, you will see that we have the parameters. Each of the categorical variables is presented as a dummy variable. We had gender coded as 0 and 1. Then we have 0 as male and 1 is female. We have pollution level, low, moderate, and high. Then we have age, which is a numerical variable. We have here coefficients, beta. We have our p-values, and we have the exponents of beta, which in this case are risk ratios. Now, when you look at each of these variables, the categorical variables, one is made a reference category. And in this case, they have made the highest value a reference category. But when you look at the exponents of betas here, most of them are less than 1, and usually it is easier to interpret when they are above 1. So in this case, we want to go and reverse that the reference category should be 0, instead of 1. Even for this should be 1 instead of 3. So here we go to analyze, again still generalized linear models. Then under models here, under predictors, we have here options where category order for factors, we want it to be descending. Continue and then click OK. So as opposed to how they were initially, 0 and 1 as a reference, here we have 1 and 0 is the reference. Then we have 3, 2, and 1 is the reference. So betas are generally not friendly in interpreting, because when you look at our betas here, for instance, for a numerical variable, it is showing a log of risk ratio for every unit change in age. If it is categorical, the log of risk ratio for one group compared to the other, which may not make a lot of sense to maybe an epidemiologist or an biostatistician. So it is easier to interpret the risk ratios this side. If a risk ratio is equal to 1, then there is no risk between the groups. If it is above 1, there is a higher risk, whereas if it is less than 1, there is a lower risk. So let's interpret for gender here. We see that females coded 1 are being compared to males coded 0. So we can see that females here have a 31.2% higher risk of going for a doctor visit or having a doctor visit compared to male participants. And here we can see that participants with a high level of pollution exposure had 58.4% higher risk of visiting a doctor compared to those in level 1, which is low. Similar thing for participants with moderate level of pollution exposure had 47.7% higher chance or higher risk of visiting a doctor compared to those with low levels of exposure. Whereas for age, although non-significant here, but we can go ahead and interpret that for every unit increase in age, there was a 0.3% increase in risk of visiting a doctor. So that's how you would run a Poisson regression analysis in SPSS. So next we look at how you would interpret, how you would present real results for your research output. Feel free to pause the video, read through the output well so that you see how best you can adjust your work. In our next episode, we are going to look at how to run a negative binomial regression analysis in SPSS. Don't forget to like and subscribe to our channel so that you don't miss out any of these episodes. See you in the next video.